Okay, Assalamualaikum and good morning. This is perhaps the last class before the break, right? We'll continue with chapter 3. Hopefully, we might not be able to finish that particular chapter uh, before the break, but no, I guess we try. Today we're going to look at the case of geometry of lines and planes. I've already mentioned before this that uh, vectors could be given two types of call way of describing them. One is using the components, which I call algebraic. Okay, this is using components, and the other one is essentially more geometric. So essentially that talks about magnitudes and angles. So in a way, given this possibility of describing vectors in a much more geometric way, one could really use vectors to help solve geometric problems. So this is essentially the lesson that we're going to do today. So we'll look into some problems inside geometry and I'll reframe them in terms of vectors. Okay, so the first thing that we want to do is to describe the simplest thing that you find in geometry is essentially a line. Okay, so we talk about lines which is usually parameterized by a single parameter. Okay, and for this particular part of essentially a line could be a curve in general. Okay, so in other words, you have a curve which is going to be parameterized by some parameter lambda. But what we're going to do is to consider the case of straight lines to begin with in order for us to describe geometry using vectors in a much more simpler way. For curves, usually this will be in more advanced courses. Okay. So okay, what can we do with describing lines using vectors? First and foremost, we know that any point in the Euclidean space, okay, in R3, one can give those points position vectors. Okay. So a point, a general point here is essentially a general point. You can give it a position vector by writing it down in this manner. Okay, so you have just your x and y and z components multiplying their basis vectors along each what you call direction of the coordinate. Okay, so one could actually give this numerical values for this x, y, z, then that would be a position vector for a particular point. Okay, so in this diagram, for example, this is just taken from the book. So in this diagram, for example, this would be a position for the point 1 to 3. Okay, but one could simply generalize this idea to the general vector, position vector, where your x, y, z could be arbitrary. So we're going to make use of this sort of notation wise, so that your R is actually describing generally a position of a arbitrary point. Okay. So okay, here the diagram is drawn here in such a way. Okay, your R is pointing from the origin, as it should be for position vector, from the point, and similarly for this vector c from the origin to this particular point. Okay, and if you draw the line between this, no, so these are just vectors for you. So if you draw the line between this what you call points, which have one of it a specified point, the other one is a general point, then that line also will, no, one can actually give it a vector there. Okay, and essentially if you look how this is actually done, you can see the vector c plus a should be equals to the vector r. Or alternatively, since usually what one does is to have your r to be unknown, so one writes this in a different way. Oh, sorry. Okay, what I'm trying to say here is essentially one can identify what this vector a from here, sorry, getting to a different story just now. Vector a here is simply the vector r minus c. Okay, so for that matter, you can think of any two vectors in that way. For example, this is say a here, this is b here. If you draw the line in this manner, then you know this is actually that should be b minus a. Okay, so when you add up these two vectors, you get the vector a. Okay, so that is a good thing to, in a way, to memorize, because sometimes you get confused which is which. The other possibility is simply this, writing the other way around, then it's a minus b. So maybe you have some kind of memory guide to know which is which, but if you fail to remember any of those memory guides, then you just go back to the basics. Okay, so okay, over here one can now try to write down that vector a, given that I know what this vector is in terms of the coordinates and what this vector is in terms of coordinate, then I will be able to write it down in terms of this vector. Okay, over here I'm using just following the book. There are two different notations here. Here is in terms of triplet, okay, of a triplet of numbers, or in this case triplet of variables, and then here triplet of numbers. They are representing your vectors. So in other words, 1, 2, 3, for example, is an equivalent way of writing I plus 2j plus 3k. Okay, so it's just a shorthand notation. So r minus c would be that, or you can combine each of the components. So you have x minus 1 here, y minus 2 here, and z minus 3 here, and then essentially you have this. So what we have done is really to describe a line given by this vector a. How is this so? Is the fact that your 1, 2, 3 here is essentially a specified point. Okay, but you have your variables x, y, and z, so it gives you the variables that define the line. But how is it being defined? It's defined through this vector a. So this sort of gives you a kind of a way of parameterizing how the line should be, where the line should be pointing. Okay, so that is essentially just an intro for this thing. So we're going to do this more properly. So here we, for simplicity, we start with a line in 2 dimensions. Okay, so you have line in 2 dimensions given a particular slope. So this slope would be a kind of parameter here. Okay, and then it will pass through some specified point x naught, y naught. So from high school algebra, you know that to get the slope, you just take the difference between 2 points for a straight line. Okay, between the 2 points on the line divided by what you call another the x coordinates of the 2 points on the line. Okay, so that will give you the slope. Okay, so we can use that to get the equation of the line in a way. So what happens over here is a description of the previous picture that we had, where a particular vector, okay, over here the vector A, previously it was that thing here between the 2 points. Here I'm just saying that, okay, I'm going to consider a line that is parallel to this particular vector A. Okay, so in other words, what happens over here, the way to think about this is to think of the same equation that we had earlier. Okay, so here previously was R, and this would be say like R naught. Okay, and then essentially the vector, the vector A. Okay, so but over here it's not quite that. Okay, what's happening here was just this vector is only specifying the direction. It doesn't have the direct connection with this R0 and R. So it's just saying that, okay, I'm going to write a particular vector that is directed to this particular what you call specified vector A. So what does that say here is essentially to say R minus R naught is going to be parallel to the vector A. Okay, so if you have remember previously when we talked about parallel vectors, then essentially the components over here and the components over here, if we take the ratio of each corresponding components, they will have the same what you call ratio. Okay, so in other words, we can use that knowledge of about the geometry information of vectors to write down the following. So I have my A given by these components A and B here. So you have to take the ratio between the two. So I have x minus x naught, taken the ratio with A here, and I have that, and that should be equal to this component, taken the ratio with your B. Okay, so that is just from our knowledge about parallel vectors. Okay. So, okay, what do we have here? We have essentially an equation for which you can actually try to rearrange things, and then you will back to the we get back to the idea of the general the equation of straight line. Okay. In fact, the B over A here specifies the slope. And where's the B and A coming from? It's coming from the specified vector. Okay. So again, given that we are just doing this two-dimensional case, but there's nothing to prevent you to generalizing this in terms of 3 dimensions. Okay. So in other words, we have now a way of writing down. Oh, okay. Before we do that, we go to 3 dimensions. Another way to think about this is to write this in terms of parameterized equation or parametric equation. Remember, the line is always given by a single parameter, say t. So I can really write in terms of the proportionality earlier, or the parallel equation thing. So I just write down t as your constant of proportionality, then I will be getting this, okay, and I can rewrite this in terms of that, okay, which would give you a set of parametric equations that defines the line, which is that, okay. And no, this can be convenient, okay, to write this line as a set of parametric equations. But if you want to get back to this original equation of a line, you can just simply eliminate t over here, then you get back to your original equation that gives you something like here. Okay. All right. So now we can go to the 3 dimensions. Okay. So I introduced initially how the concept of parallel vectors that can define a particular equation of a line. Okay. So there are 2 ways. One is using that over here. The other is using this parametric equations. Okay. So now we can generalize this idea to 3 dimensions. Okay. So for 3 dimensions, we use the same thing. The fact that this vector over here, if it's parallel to that, then the ratio of these components okay, these should be the same. Okay, so in other words, now we can actually write down the equation of a straight line in 3D by just writing down the ratios of those components. And of course, if you want to put some numbers here, you can, because you only have one parameter to describe the line. Okay. So this would be the general case, but it is possible that your vectors here, say you want to find equation of line of parallel to, say, vector A, but one of the components of A is 0. Okay. Then what one just needs to do is to go back to the original idea of this being parallel. Okay, so the only the only thing that can happen over there, if you look at this again, since they are parallel, this component ratio with that, this component ratio with that should be equal. So that gives you that. But the other one, okay, since this is going to be proportional to A, B, 0, the only way that this can be proportional to that is that Z equals to Z0. Okay. So in other words, there will be cases where you have 0 components for the specified vector, then you go to this particular set of equation. Okay, or generally we can do that. Okay, so it depends on what equation of line and what is the specified direction being given. Okay, now as I said just now, there are 2 ways of describing vector. One could actually write the case where in terms of this equation over here, or this equation, the earlier equation, sorry, this equation over here, or one can write this no, to be equal to some parameter over here, then you'll be able to write this parametric equation. And in terms of parametric equation, if you have one of this a, b, c to be 0, that's no problem. Okay. All right. I hope that will be good enough for you to be able to write down equations of lines parallel to a particular vector in generally in 3 dimensions. Okay. Now, lines are not the only object. Lines is the simplest object in Euclidean geometry, but no, if you go beyond a line, there will be a plane, for example. Okay, so how do you describe a plane in 3D? Let's consider the case where you limit yourself to the 2-dimensional case first. Okay, so you consider the point x0, y0. So x0, y0 has to be in the plane, so it's in the plane. And to be able to describe the plane, usually there's one normal vector sort of sticking out with the direction of 90 degrees perpendicular to the plane. Okay, and that would be our what you call way of characterizing the plane from the normal vector. Okay, so now what one does is, okay, since this is 90 degrees, and okay, I forgot to mention this now. So here's your specified point on the plane. So here is essentially the plane is the plane z equals z0 here. Okay. So here's a specified point. Here's an arbitrary point. So you take the difference between the two position vectors, then you have this difference between this. So this is r here. Let me try to draw this. So I will assume there will be some origin here, so there will be an r here. Okay. And there will be an r0 here. Okay, so that vector will be r minus r0, just like before. Okay, so then since this is 90 degrees or perpendicular to that particular vector on the plane, in the plane, sorry, that is 90 degrees pointing out of the plane. So then we have from vector algebra that we know, if you have two vectors perpendicular to each other, then their dot product or the scalar product is going to be equal to 0. Okay, so in other words, the equation of the plane, you just substitute what r minus r0 is. Basically, in this case, no, your z component doesn't play a role because it's everything is z equals z0 plane. Okay, so then you just simply have the case of a from the normal the x component of the normal times with this x minus x0 plus b with the y component of the normal times y minus y0. So this would be the equation of the plane, which probably you have seen before. Sorry, am I using So this should be the equation of the plane. And if you try to rearrange that equation, then it looks similar to this line. Now, why is that? So the explanation is actually understood from here. So here is essentially what happens over here. So here is your line on the plane or in the plane, and that will be the normal. Okay, and the normal is actually specified by your A and B. So if you have A and B over here, then this would be, let me just do this properly. Yeah, this would be your cos phi, right? Sorry, tangent phi. Sorry. Tangent phi equals to your y component divided by your x component. Okay, and that is not the slope of this line. Okay, but how is this appearing here? Okay, and it appears not in this manner. Okay, but it's sort of reciprocal of that and with a minus sign. Now the way to understand that is to think of, okay, what's the angle between the line L with the x-axis, for example. So it will be this theta here. And what is theta over here? Theta is simply your phi. And remember that this is perpendicular. So it would be phi plus pi over 2. So if I really want to have the slope of this rather than the slope of that, okay, then I would actually use the tangent theta instead of tangent phi, right? This tangent phi give you the slope of this normal vector. Tangent theta will actually give you the slope, okay? And we substitute theta here to be phi plus pi over 2, okay? And then okay, your tangent is sine over cos, and then you have this addition formula that you can actually use. Okay, and when you do the addition formula, you'll find that this simplifies to cos over sine with a minus sign underneath, and that is essentially your cotangent now given by this minus a over b. Okay, so that is how it seems like two different geometric information comes together in this particular case. Okay, so it looks like equation of line, but it's actually describing the plane. Okay, what else? Okay. So the next thing to do is now, okay, we have sort of specified our line just now inside a particular plane, which is z equals z0. One can now just put back the equation of the line all together over here, so that this now becomes the vector in 3D. And then you generalize your normal to the plane as a as this vector with three component things. Now the one before essentially your normal before. Okay, if we look back to this picture earlier, this is already how should I say, just give me a minute. I'm getting confused now. Yeah, okay. Your normal there is already pointing just check. Getting confused a little bit. Your normal there is already in the k direction. So in other words, what happens over here, the combination over here should somehow produce a normal pointing in k direction. Okay. So that is what happens over there. So generally, one could have the normal pointing in any direction. Okay. So then you have this to be generalized to that. Okay. I hope that's clear to you. It can be tricky. One of the things with geometry, it requires a bit of an imagination. So this is probably one of the, not to say difficult, probably one that requires a little bit of imaginative mind to be able to see the type of problem. Okay, never mind. So the idea here is now we generalize that example before, which is restricting your vector to be on the plane, and then use the vector directions to actually find the equation of a plane. Okay. So over here, we generalize it to the case of 3D, and you still have the same equation. Okay. There will be a normal, and then whatever vector inside the plane given by this r minus r naught, when you take the dot product, it always gives you a 0. Okay. So then, okay, I can simply just plug in now these two expressions for r minus r naught and n, and essentially we get the equation of plane. So here you can see that your normal sort of parameterize your equation of the plane here. And what is this d coming from? The d is coming from your x naught, y naught, and z naught multiplying the a, b, and c. In fact, you can calculate it out to be that. Okay, so that essentially how you'll be able to use what we know in the previous case to generalize it in 3D. Okay. So let's look at some applications of the things that let's remember, okay, the simplest object in 3D is a line, and then the next what you call geometry object will be a plane. What's the next object? It will be the whole space. Then you don't really need finding a particular equation for that. Okay, so we only have lines and planes that one need to worry about because they are subset of this three-dimensional space. So okay, let's look at some example and see how we can actually use the information from vectors as a geometric objects to find equations of planes and lines. Okay, so here's the first example. I think this is again just taking it out from the book. Okay, find the equation of plane through 3 points. So you have A, B, and C. So what can we do with this? Well, the first thing to do is to find the vector in the plane. Okay, remember the r minus r naught before. Okay. So what can actually, how can you actually get that? Well, the vectors in the plane can be obtained from these 3 points. Okay, for example, I can consider this is b minus a, for example. This will give you b minus a. Okay, and this is c minus a. So that will give you the two vectors. Okay, two vectors in the plane. What can we do with this? It's not okay. The other, okay, maybe I should explain what we're doing. Here is a general vector in a plane. Why this is general in a vector? Because you have an unspecified position vector here. Okay, here are two specific vectors. We should write specific, which is given through the points given in the example. Okay, so they don't make up this one, but what can we do with these two vectors? Well, we can find the normal, because you know that two vectors in a plane, take the cross product, I will get a normal. Okay, so this is your AB, your AC, for example. Okay, so I can do this cross product, and I will get essentially one part of the information that I need, okay, to define equation of plane. Because I will do this n dot r minus r naught thing. For this, okay, now what is r minus r naught? Well, in this particular case, you just need to take any r naught. Hello? Is there a question from somebody? I thought I heard some voices, but okay. Where are we? Oops. So what would be r minus r naught? Well, r will be the arbitrary position vector. R naught can be any vector. Okay. So we have three possibilities over here. I can use this position vector, I can use this position vector, or I can use this position. So in this example over here, what did I do? In this example, I use B. Okay. Then I just put that in. So this is your coordinates of B, 2, 3, and 0. Okay. And your n is already given from here. And you can simplify this equation and reduce to that. Okay. Now, it seems a bit arbitrary at this particular point, since I'm choosing a particular position vector r naught here. Okay. Now I want you to do the exercise, even if you choose A or C for this particular case, you'll be getting back to this simplified equation of plane given here. So that I leave as an exercise for you to do. Okay, just to verify that. Okay, what's next? Let's do another example. Here, essentially, you want to find an equation of a line through a particular point here, but perpendicular to the plane in example 1. Okay, so the plane is example 1, is characterized by this normal. Okay. So one has to understand again, no, when it says equation of a line perpendicular to the plane. Okay, so here's the plane. Okay. That whatever line that's supposed to be, it has to be perpendicular to this plane. So in other words, it has to be parallel to this normal. So it's parallel to that normal. Then I go back to this particular set of equation where, okay, since it's r minus r naught is going to be proportional to n, so I can use that okay, the respective components, their ratios will be equal. So I get what? Well, r naught is coming from where? R naught is from the given point. So x equals 1 and y equals 0 and z equals minus 2. So we can put that there. So I have, so that means I will have x naught 1, y naught 0, z naught 2, and I use this ratio thing of this respect to that, so I get that. So this is 3 x minus 1 is 1, okay, over 3 must be equals to y minus y naught, which is that, which is y divided by minus 4, which is that, and so on and so forth. Okay, so that is quite a simple problem for this case, because you are given the direction of the line to be pointing towards the normal. As I said before, one can either use this or one can use the parametric equation. Parametric equation is now simply just, it comes from this, r minus r naught proportional to the normal, but now I can multiply a parameter to the normal. Okay? And that will reduce to that. Right. The other thing that one can also use, so these are getting equations of lines and planes in the previous example, okay? And one could also do some other things with respect to, instead of equations, you want distances. So how do you get distances? Well, you just find the appropriate vector and find their norms. Okay. So here is a particular case of trying to find a distance from a particular point P, okay, to a plane. Now, what does that mean? No, for the plane there are many different points that you can actually choose. Okay, but what does it mean by the distance between a point to the plane would be the perpendicular distance. So this is the perpendicular distance. So all we need to do now is to be able to see, okay, can I find the vector PR, okay, given some information about the plane. Okay, so in case usually you do not know this point, usually unknown. Okay, but you might be given another specified point. So given that situation, then probably one needs to be able to this vector first, and then deduce the information about this vector PR. Okay, so that's what we're going to do. Okay, so we pick any particular given point on the plane, and that will give you a vector PQ, and okay, what else do we need? We need the angle. Okay, we need the angle. So the angle should be known. The angle should be known. So that means we need to use a particular information about the geometric information about these vectors here. So how do we get that? So you can see easily what we need is this PQ. So if this is the angle, this is angle theta here. So then PR, the perpendicular distance, is PQ cos theta. So now the question is how to get this theta. So the way to do this is to consider, remember, the cross product. Dot product. I'm getting confused now. The dot product says what? Vector A dot vector B should be equals to modulus A modulus B cos theta, right? And that would be our way of getting that cos theta out. So in this particular case, what do I need is essentially a vector that gives you this magnitude here, and then another vector gives you magnitude here. So what are these possibilities that we can do? Well, we have to use the PQ. Okay. P is given. This is given point. Q is also given as a point on the plane. So we can get PQ to be one of the vectors. Okay, so that that will solve the problem of one of these vectors here. But we need another one. Okay, and we need that PQ, by the way. We need that PQ because we want to have PQ cos theta. But what is the other one? The other one would be coming from the normal to the plane. And what we need in this particular case, that this normal needs to be normalized. So in other words, what do we have here? So let's do this. Okay, here we have your PQ. Here you have your normal, right? So now if your normal is not normalized, then I will have some numbers here. If your normal is normalized, say to this unit vector here, then PQ dot n, okay, PQ dot n, so now normalize that to give you n here. PQ dot n will be the length of the unit vector normal, which is 1, and then your length of your PQ, which you can actually derive, okay, and you get your perpendicular distance, okay, your PR. So that is essentially the trick that one can actually do. I hope this is a little bit, I think you need to imagine a little bit what's going on in terms of geometry. So let's look at an example. So here is given a particular point, and you want to find from this point to the plane which is given in terms of this equation. Okay, so how can we do this? Well, in the first place, remember we need to have PQ. Okay. P is given here, but what's Q? Well, the problem here, Q is not even mentioned anywhere inside this input data that you're supposed to have in the question, but we do have this equation. So I can now try to find, okay, whatever x, y, z that satisfy this equation, okay, will be a point on the plane. So for example, over here, I can choose q goes to 1, 2, naught. So I put 3 times 1 times 2 times 2, and then this is 0. So I get what? 3 minus 4 plus 1. This is a point chosen, but no, one could replace this with other points if you want to, as long as it satisfies this equation of the plane. That should work, and I'll leave that as an exercise. Okay. Find a different point. So let's stick to this point Q equals to 1, 2, naught. So what do I have? So PQ will be this. Okay, it will be the difference between Q and the point P. Okay, remember that the equation thing before. Okay, so this would be Q, this would be P. So Q minus P gives you PQ. Okay, so then one can just take the difference between the components there. So I have 4J minus 3K, or actually in terms of the triplet of numbers, is that. Okay, so I have PQ. Now, what about the normal? Okay, remember we need the normal here. Well, the normal comes from the equation. Remember, the equation is what? N dot R minus R naught should be equal to 0. Right? So in this particular case, this N is those numbers that appears multiplying the variable. So in other words, that normal can be given by, if you look, what's the number again? 3 minus 2, 1. So it's 3i minus 2j plus k. However, this normal is not normalized, meaning it's not unit. The norm is not equals to 1. Okay, so you need to divide it by this number, which is the norm of this this vector here, and then basically you can get your your normal, unit normal equals to n divided by the norm of n. Okay, so now one can just simply plug in. Okay, this is your normal. Okay, divide by the norm and your dot product between PQ and the normal. So this is your PQ. Okay, PQ was calculated earlier to be that. And that should be giving you the distance from that point to the plane. Okay. One could also do this for the simpler problem of finding the distance from a point to a line. Okay, so the technique should be similar. So you have this point. Okay, on the line, just like before, there are many different points on the line. So which points do you want to use? You want actually the perpendicular distance, where it's the shortest. Okay, so there again you just need to find Q here, and then in this particular case you just use the sort of equation of the normal in this slightly simpler what you call context of a two-dimensional case. Okay. All right. I think this is actually given down here. Okay. So here is actually QR. Okay. And then what we need in this particular case is a unit vector. So then over here this, okay, so this is your QR here, this vector there, but what we need is this perpendicular distance, and that is proportional to sine theta. Okay, so what is the geometric formula that gives you sine theta? Is essentially your cross product. Okay, so there again you use the same trick. So what we need is something finding out the right formula, the right vectors here. So here would be your u here will be the unit vector pointing along this direction, and PQ is coming from this line here, or from this vector here. Okay, and you use a cross product, and then essentially you get your perpendicular distance. I'm running out of time, so I probably this is the best place to stop. So we'll have to continue probably after the break. And remember, we need to replace one lecture at least. Okay, I hope that should be enough for today. So let me take the attendance now. Okay, so let me just mention there should be one SCL module to be given to you. I'll probably announce this probably at the end of this week, okay, to give it to you. Otherwise, if you don't hear from me, because I need to finish marking your exams as well by this weekend. So if you don't hear from me, then probably we have to shift the SCL module after the break. Okay. So okay, thank you everyone. Okay, bye.